All right, so I got a few emails with questions about this particular problem in Cal 1. So what we have is we have a path, okay? And I think the path is y equals what? X squared minus 7, okay? So we have something traveling along this parabola. And then we have a position. Okay, and the position was 0, minus 6. Okay, so this is an xy position, right? And if you can see that this was on the board before, it was originally not my intention to do repeated takes of these videos. I'm just going to do them, but I had a disaster, so yes, this is the second time I've done this. Okay, so so we have something moving along this parabolic path, and then we have this position, and the question is, where on this path is this particle, or this thing that's moving, closest to this position? So this is of interest because if you have some, let's say you have something that's moving, relative to your position, and you would like to know when it has the closest proximity, because you want to contact it, or maybe there's something that's going to be exchanged, or whatever, right? Some kind of interaction, and where that proximity is at a minute, is at a minimum, is of interest. I hope that the vocabulary we're using here is indicative of an optimization problem, right? We're trying to find when the distance to this thing is a minimum. So it's an optimization problem. So we need an objective function, and we need a constraint, and we need for that constraint to appear inside of our objective function. Once we have that, then we do some steps, yeah? You take the derivative, set it equal to 0, and solve it, and from there on, that's pretty mechanical, yeah? But the setting up of the problem is what we really want to focus on. Because, we're trying to become better problem-solving strategists, right? That's what we're after. So, first of all, I'm describing this as a path. My bouncy board, I'll fix that. I'm describing this as a path. It doesn't really look like a path, it's sort of theoretical, right? When you think of a path, you think of like a little clearing through a park or a forest or something, right? A path. And this doesn't look much like a position or a place. So let's draw a picture of this thing, and let's get our visual processor to work for us on this, and we'll proceed from there. Okay, so let's see. So we're going to need a coordinate system. X squared, just a smiley parabola, minus 7. It's just shifted down 7. So 1, 2, 3, 4, 5, 6, 7. Negative 7, okay. 8, 9, that's 2. 1, 2, 3, 3. So this point is going to be on the path. 1, 2, 3, that's negative 3. So this point is going to be on the path, okay? And so this path is going to look something like something like that, right? Not very good, but basic idea. So this thing is, let's say that it's moving from left to right, so it's coming down here, and then it's going to come over here, it's going to swing around through this point, 0, negative 7, and then take off that way, right? And our position here is 0, negative 6, so that's going to be right there. So what we want to know is, when is this particle closest to this position, okay? Well, let's see if we can identify an area of interest, or a domain where we're pretty sure our answer is going to be, right? It's going to be in this square. You see that? It's definitely not out here somewhere. This is all far away from our position, yeah? So let's just focus on this square and see what this can do for us. Now, if this was at the origin, right, a parabola goes through 1, 1, which would be here, yeah, negative 1, 1, 1, 1. So we know that this square is where it's happening. So let's just look at that square, okay? Okay, so we get rid of the distraction of the big graph, looking at the whole path. We're not really interested in it. So this is our y-axis here, yeah? This is the point, what, 0, -7. This is the point 0, -6. That's our position. This is going to be -1, -6. And this is going to be -1, -7, right? And our parabola is in here like this, something like that. And what we're looking for is the point where it's at a minimum distance here. So we know that this distance here is 1, yeah? From here to here is 1, and from here to here is also 1, okay? And so it looks like it probably gets closer, you know, somewhere around here. This is an estimate, something like the diagonal, right? So what we want is, we want the xy coordinates of this position right here. Now, these distances are easy to get because they're horizontal, right? This is 1, and that's 1, it's vertical, it's easy to get. This is at a diagonal, but that shouldn't bother you. That should make you think right away of a hypotenuse of a right triangle, okay? So if we draw our right triangle, yes, notice that now, you know, this distance right here, which is what we're interested in, that's actually our x-coordinate, okay? Remember that this path is x squared minus 7, yeah? So what we want is this distance, yes? So if the distance from here all the way up to the x-axis, that's going to be x squared minus 7 for whatever x is, right? If we subtract 6 from that distance, we'll get just this piece right here, right? But this is negative. This is negative. If you subtract that, it'd be like adding, right? So I think this distance right here is going to be x squared minus 1. Verify that, okay? But that is going to be that distance. Yeah. So this is our right triangle, okay? And now we need a relationship that uses these values, right? Well, we said the Pythagorean theorem should come to mind, right? So that's what a squared plus b squared equals c squared, yeah? And there's a picture that comes with the right triangle, a, b, c, okay? So c is going to be, in this case, it's going to be our distance, yeah? That's what we're trying to minimize. So to use the Pythagorean theorem with this triangle, we've got d equals the square root of x squared minus 1 squared plus x squared, right? All I'm doing is I'm using the Pythagorean theorem, plugging the specifics of this triangle into it. This is what we want to minimize. Now, if this is what we want to minimize, actually we're done, right? All we have to do now is take the derivative of this and set it equal to 0. Notice that, you know, our constraint appears here in our objective function, okay? Because, you know, the actual path of the particle is described by x squared minus 7, and this has this 6 in it. So we have our constraint in there. We have our geometry. It's all ready to go. We just take the derivative and set it equal to 0. I'll leave you to do that. It's pretty mechanical. It'll give you the opportunity to use some of your 9 derivative rules. If you have any further questions about this problem, feel free to email. But for now, I think that's where we're at.